Hello everyone and welcome to this talk. Today I'm presenting you how we can identify sensitive URLs at web scale. This is joint work with TU Berlin, the Cyprus University of Technology and the IMDEA Networks Institute. In recent years, we have witnessed the creation of novel regulations that define new standards in terms of data protection and electronic privacy for users that surf the web. The most prominent examples are the European General Data Protection Regulation, active since June 2018, and the California Consumer Privacy Act, which became effective in January of this year. Those regulations define new concepts such as personal data that belongs to the user, and they clarify that the user has to grant explicitly his consent before his data is processed. The organization that processes user data is also responsible for protecting it adequately and do not redistributing it. Because of these innovative features, the GDPR became a model for many new national laws outside the European Union, including countries such as Brazil, Korea, and Japan. Even if these regulations were enforced only in the last 2 years, they already account for some extremely strict fines that were issued to several organizations. In the case of GDPR, in this timeline, we can see some of fines that were issued in the last year after user data ended up shared with third parties as a consequence of a data breach. Since the regulation is very well defined and it clearly sets what are the duties and the obligations of the different parties, these fines are pretty high and they can go up to almost £200 million in the case of the British Airways example. Unfortunately, even if legislators clearly explain who are the categories of interest of new regulations, it is not very clear how do we proceed when we have to check who is actually affected when a new regulation comes out or an old one gets updated. Well, it turns out that each time that we have to perform these kind of checks, we do not have any automatic tool that can assist us with this task, and we end up resorting on manual analysis to find which are the services that are affected by the regulation. So let's quickly see who could benefit if automated tools for checking compliance with new regulations were available. We have the legislators themselves, service and content providers, as well as users. But they're not the only ones, because also researchers that study privacy issues and censorship practices on the web need to categorize the web pages that they analyze. To achieve their goal, those researchers end up relying on services which were not developed for categorizing web pages. The most popular solutions include Alexa Ranking, that provides categorization at the domain level, or the McAfee Trusted Source, which is a reputation system for IP addresses, domains, and URLs. In an attempt to overcome the lack of freely available systems for categorizing web content, we decided to create one. We use GDPR as a model to define the categories that our classifier can detect. And we choose such categories because of the special requirements that are needed when service providers need to process data that belongs to those categories. In addition, we also wanted our system to work at the level of individual URLs and web pages, rather than providing a categorization of domains and IPs. Finally, we decided to create our classifier using exclusively open source data, in order to allow other researchers to reproduce our results and to build on the top of them. Once we created the classifier, we use it to estimate the percentage of sensitive web pages according to GDPR that are available on the open web, and to understand if those web pages with sensitive content are treated differently from other web pages. So let's start with the first part and let's see how we can build a classifier for the GDPR categories. In this blue box, we have the first recital of the Article 9 of GDPR, which states that service providers are not allowed to process user personal information which belongs to the categories mentioned in this text. Here, those 5 categories are indicated in bold, and we call them sensitive categories. Namely, they are ethnicity, political beliefs, religion, health, and sexual orientation. The first step for building our classifier is generating a rigorous definition of the categories, starting from those very broad notions that in the recital are identified only by a single term. This means that we need to solve what we call the ambiguity issue. Depending on the context, the same term can refer to different things. For example, the word health can refer to human health diseases, animal health, or recipes for a healthy eating. We also need to keep in mind that to run our classifier, we will need a ground truth, and the organization of the ground truth is extremely important. Having less generic classes means that it will be more likely that the ground truth contains ambiguity. On the other hand, using many classes would result in an excessively specific dataset that might not be easy to map to the 5 GDPR sensitive categories. Another challenge is how we can build a reliable training set for a classifier that should be run on the web. We need to make sure that the training set is large enough in case we want to be able to classify generic web pages. Similarly, if our goal is to understand how many sensitive content we have on the open web, we will need to collect several million of web pages that will be feeding input to our classifier. This means that we might encounter issues both at the moment of storing and processing such a massive amount of data. To train our classifier, we use the dataset made available from the Curly project, which contains high-quality human-labeled data. Curly is the largest publicly available taxonomy of web pages, and it contains over 3 million web pages that were manually labeled by 90,000 editors. Those web pages are spread across 1 million different categories, which are organized into a hierarchy. We focus only on English content, and for this reason we use half of those URLs and around 300,000 of the categories. A big challenge that we had to face when we decided to use the Curly dataset was to understand how we can map the 300,000 Curly categories to the 5 GDPR categories that we want to be able to detect with our classifier. This process requires some manual validation. For this reason, we decided to focus only on the Curly categories that contain a high number of URLs. In this example, we can get an idea of our technique. On the left, we have the Curly categories with their branches, and in the brackets we have the number of URLs that belong to each category. We start by generating a list of keywords that are extrapolated from the branches' names that appear in the category hierarchy. Then, for each keyword, we perform a cumulative sum of the total number of URLs that are associated to this keyword. In the example, we see that the keyword health appears in the name of all of the categories except the first one, and thus the corresponding number of URLs identified by this keyword is 1 plus 4 plus 5 plus 2. On the other hand, arts is included only in the first category, and for this reason it maps only to 3 URLs. We apply this process to identify the most representative keywords in the Curly dataset. Now, let's see how we can leverage this process to identify the Curly categories that are related to the 5 GDPR sensitive categories. We start by creating a crawler that we use to download all the English content from Curly. Next, we use the process that we just saw in the previous slide to build a mapping from keywords to the number of URLs. After we know how many URLs are associated to each keyword, we filter out the keywords that are included in categories with less than 100 URLs. This process leaves us with a set of 5,100 keywords that we manually inspect. This means that we go through this long list of keywords and we select only those that can be put into relation with one or more GDPR categories. For example, religion and spirituality, substance abuse, association, all those keywords can be related to some GDPR categories. While the first two are very specific, the term association could refer to association of dentists as well as student associations or to a political orientation. The 300 keywords that we select from this manual analysis identify a subset of the 300,000 Curly categories. In the fifth step, we manually inspect this subset and we label those categories that can be put into relation with one or more of the GDPR sensitive categories. To confirm this mapping, we check the names of the subcategories, we look at the information in the path and the parameter of the URLs, and we also sample web pages for the categories where we could not decide with other techniques. At the end of the process, we generated a set of over 200,000 URLs, which are labeled with one or more GDPR sensitive categories. In the next step, we remove the multi-category elements and we download the content from the corresponding web pages. It is interesting to highlight that, as side effect of our manual validation in the fifth step of this approach, all the URLs that were selected but that ended up not belonging to any one of the 5 GDPR sensitive categories are added to a special 6th category, where we include all the non-sensitive content. In this table, we can see how the URLs from which we downloaded the content are spread across the 6 GDPR categories. To build a classifier, we use a multinomial naive Bayes algorithm, which allows us to train a single classifier that can predict multiple classes. We choose this algorithm because it is easy to train, it was previously tested on the Curly dataset with good results, and it is very fast. In the next slides, we will see why this last detail is extremely important. Next, on all the downloaded web pages, we apply the standard preprocessing steps, such as stemming and putting all the content in lowercase, before deciding what part of the web page we are going to use. We can choose among the actual content of the web page, the information contained in the meta tag, or a combination of the two. Similarly, we also test several feature engineering algorithms to select which one will give us the best results. Here we include only the details for the 3 best performing candidates. As final step, we set the feature vector to have a maximum length of 5000 features. In the table at the bottom of this slide, we can observe the overall accuracy of the classifier with different combinations of input data and feature engineering algorithm. The highest accuracy that we obtain is slightly above 83%, and we get this value when we combine TF-IDF using information obtained from the web page content and the meta tag. We built our baseline classifier using this particular combination of feature engineering and input data. In the chart at the top of this slide, we report the precision and accuracy curve for our baseline classifier. As you might notice, the classifier has some limitations. First, if we check the table at the bottom, in blue now we can see the overall amount of URLs that belong to any one of the 5 sensitive categories. If we compare those elements with the non-sensitive ones, we will realize that our training set is unbalanced because sensitive elements account for 2 times half the non-sensitive ones. Second, we are not fully using the Curly dataset. Of the 1.5 million English content on Curly, we only included in our dataset around 200,000 URLs. Third, if we check the precision chart, we will notice that our baseline classifier has low precision on categories such as non-sensitive and sexual orientation. So what can we do? How can we fix those issues? We use a well-known approach in machine learning where you augment your training set by running the classifier on elements that were not part of the ground truth. So we use our classifier to categorize URLs that were not selected during our manual validation process, and we repeat this process until we reach the same amount of sensitive and non-sensitive URLs in the training set. Before adding new URLs to the training set, we sample a few hundred elements to check that they were correctly categorized. In the final URLs column of the table, you can see the results of this process. We observe that using the new training set, the overall accuracy of the classifier increases by 5% if compared to the baseline classifier. We use this new training set with 440,000 URLs to create a second classifier, which we will call Balance Classifier. As you can see, if we compare the precision chart with the new classifier with the old ones, the precision remains stable for 4 of the sensitive categories, while it improves for non-sensitive URLs. Unfortunately, even with the Balance Classifier, the precision for sexual orientation category remains around 70%. But rather than a limitation of the classifier, this might be an artifact of the training set, and the fact that it contains less than 4,000 URLs that belong to this specific category. Now that we have a classifier, let's see how we can use it to estimate the percentage of sensitive content on the open web. The first thing that we need to decide is how we can efficiently sample the web. How do we choose which websites to crawl? How do we store the collected data? Instead of reinventing the wheel, we choose to use a service with more than 1 decade of experience in crawling the web. We rely on the Common Crawl project, which periodically crawls the web and releases all the collected information in form of monthly snapshots. We downloaded the snapshots from October 2019, which contains 3 billion web pages and consists of more than 280 terabytes of data. So now we have solved the problem of collecting the data, but we have to understand how we can efficiently process this snapshot. To give you an idea of the amount of data, for 1.15 billion web pages with English content that are available in this snapshot, we could not load in memory even the corresponding list of URLs if we were using a machine with 256 gigabytes of RAM. To overcome this issue, we perform some heavy optimization, like for example, uncompressing the archives only in memory, and those optimizations allow us to classify the entire snapshot in a little bit more than 3 days using a single commodity server. The Common Crawl snapshot contains around 1 billion web pages fetched from 15 million different domains. This pie chart provides an overview of the distribution of the different sensitive categories across the entire snapshot. We see that not all of the categories are equally represented. The most popular one is health, which appears in 7.1% of the web pages, followed by religion and political beliefs. The sensitive URLs were detected on 4.3 million domains, which means that almost 1 domain out of 3 hosts at least one sensitive web page. The distribution that we see in the pie chart is when we consider all of the sensitive content, but if we restrict our interest only to dedicated domains where all of the content belongs to the same category, we would have a ranking which is slightly different from the one that we see in the slide. In presence of domains where all of the content belongs to the same category, sexual orientation has 45% of its URLs fetched from dedicated domains. But sensitive content is not hosted only on dedicated domains, and when a domain contains at least one sensitive and one non-sensitive URL, we say the domain has mixed content. Domains with mixed content have usually up to 20% of their URLs flagged as sensitive, but in case the homepage of this website is also sensitive, then the amount of sensitive content can go up to 70% of the overall content. In presence of domains with mixed content, any service that categorizes the domains instead of individual URLs will erroneously flag at least one web page. Now that we know the amount of sensitive content that we have in the snapshot, let's see if those web pages are treated in a different way from other type of content. We first analyze the protocol that the crawler used to fetch the content for a particular web page. Across the entire snapshot, we observe that the amount of URLs that were downloaded over HTTP is approximately 28%. And this percentage also is very close to the amount of sensitive URLs that were downloaded using the same protocol. The black horizontal line in the chart denotes this percentage. We split the URLs into categories, and we also group them into URLs that were served from dedicated and non-dedicated domains. In the chart, URLs of dedicated domains are marked in orange, while in blue we have all the URLs that belong to a particular category. The first thing that we observe is that there are some differences, and those differences are consistent across all of the categories, depending if the URL is accessed or not from on a dedicated domain. For all of the categories on dedicated domains, URLs are more likely to be accessed with HTTP. Possible explanations of this phenomenon are the dedicated domains. In case of dedicated domains, we observe less URLs, or that hyperlinks within a website more often appear with the HTTP protocol. A second observation regards the fact that two of the sensitive categories, namely ethnicity and sexual orientation, have many more URLs that are offered through HTTP. And in this specific case, almost 50% of the URLs, independent if they are on dedicated or not domains, are offered with the HTTP protocol. Because of those trends, we conclude that there is no evidence that owners of sensitive content are putting in place special measures to protect the privacy of the users that access those web pages. Specifically, with regard to the protocols, service providers seem to do not even follow the best practice, such as offering content through an encrypted connection. As second analysis, we inspect how web pages with sensitive content handle cookies. In this case, we do not restrict our attention to third parties, but we check also what happens with first-party cookies. We check third-party cookies because those cookies are often associated to advertisers, and they could be used to track users across different services. Because of this, nowadays major browsers such as Safari, Google Chrome and Firefox by default they block this type of cookies. Similarly, in some cases also first-party cookies might be seen as an invasion to users' privacy. For example, in 2009, Spain fined the Vueling airline because on their website the company failed to obtain valid consent before processing the cookies that were collected from visitors. To analyze how web pages with sensitive content handle cookies, we sample around 700,000 URLs across different categories, and we visit them with a fully fledged browser. All the data collection was performed from countries within the EU zone in order to obtain the minimum amount of cookies, and for each web page that we visited, we never gave any consent to have cookies installed in our system. After we obtain cookies, we inspect them with the cookie check tool, which allows us to distinguish among trackers and non-trackers and to detect persistent cookies. We consider persistent any cookie that has a lifetime exceeding 1 month. In this chart, we can see how cookies are managed across different categories, and in the bars with the diagonal lines, we see the persistent cookies, the amount of persistent cookies. As we can see, there are not big differences across categories, and if we do not make distinction on the origin of the cookie, on the average 71.5% of URLs serve at least one persistent cookie. When we focus on third-party cookies, which are the red, the orange and the red bars in the plot, we see that around 49% of the websites serve some third-party cookies. 87% of those cookies are persistent with a lifetime that exceeds the month. According to Cookie Check tool, the most tracked sensitive categories appear to be political beliefs and sexual orientation, but also in this case we do not observe huge differences compared to other categories. Similarly, as we did for the analysis of the protocols for sensitive and non-sensitive URLs, we conclude that also for cookies there is no evidence of special treatment reserved to web pages with sensitive content. To recap, in this talk we have seen how we can build a classifier using the GDPR definition of sensitive categories. Our classifier is able to categorize individual URLs using only information obtained from the content of the web page and is trained using publicly available open source data. We use this classifier to study the amount of web pages with sensitive content that are available on the open web. To this end, we leverage data from the Common Crawl project to classify 1 billion web pages. In the Common Crawl web snapshot that we analyzed, we observed that sensitive web pages account for approximately 16% of the content and that almost 1 out of 3 domains contains at least one sensitive web page. When we turn our attention to those sensitive web pages, we observe that they are handled in similarly as any other content, without any special provision for the privacy of the visitor accessing this type of content. In particular, we notice that some sensitive categories are more likely to serve content through HTTP. When we sample a subset of 700,000 URLs, we notice that sensitive web pages contain the same amount of third-party cookies as non-sensitive ones, and that more than 70% of cookies that are set are configured to last more than 1 month. For the benefit of other researchers, at the URL that you can see in this slide, we make publicly available our classifier and also the curly categories that we use to train it. We encourage you to download the repository, use our classifier and share it. Thank you for your attention.